Good morning, good morning. Hope you're doing all right. I hope your friends or family are all healthy. I um I left my ukulele on campus, right? It's in my office. It's behind uh, a set of books on one of my bookshelves, and that's always fun to play. Like when I'm stressed, I just close my office door if it's not office hours. I just play the ukulele by myself for like 10 minutes. I'm a terrible ukulele player, but yeah, like, well, I think I might have another ukulele. Maybe I should go find that. That's like something I can do in these sort of 2 minutes before class starts. It's maybe less awkward than just talking, I guess. I don't know. I would need to practice. You'd have to try to not laugh at me, though. If you did, I wouldn't even be able to tell. 43, 40 seconds. All right. Good morning, folks. Welcome back. It is Tuesday. I had to remind myself what day it was. Let's see. I'm not sure I'm on the right screen here. Just same communication I wanted to make sure to mention, and the key thing, of course, being there is an online quiz, so I would like you to do the practice quiz first, just so that you see the format, because the practice quiz doesn't count. The practice quiz deals with some calculus question from a while back, but just turn in something. I mean, might as well practice the question, but just turn in something and then do the real quiz. The real quiz is available all day today. Oh crap! I think I'm muted. Okay, let's fix that. Thank you. Let's try this. All right, can you hear me? Okay. All right. So, yeah, let's. So, okay. So, just a step.
All right. Let's get rid of this. Come on.
Oh, that's fine. All right. Yeah. So the online quiz, please do that today, sometime throughout the day. It could be anytime today. Please do the practice quiz or the pretend quiz first. The pretend quiz doesn't count for points, but if you do that, then you can see what the format looks like. All right. Let's see. Step forward. Okay, so just I should comment that we're not going to do a whole lot that's really new today. A lot of what you'll notice today is that the algebra game is kind of strong. So what we ended on last time was that there's this thing called an inflection point. That happens when there's a change in concavity. So if you go from concave, if the graph starts concave up and then changes to become concave down, or starts concave down and becomes concave up, right at that point where that occurs, that's called an inflection point. I do want to review how we build a sign chart for f prime. So this is kind of older stuff. This is like before spring break. To make a
To make
sign
a
chart
sign
for
chart
f
for f
prime, you need to
prime, you need to
find
find
partition numbers
partition
of
numbers
f
of f
prime.
prime.
So
So
the x
the x
values that you
values that you
mark
mark
on
on
your
your
sign
sign
chart on
chart
your
on
number
your
line
number
should
line
be the
should be the
ones
ones
where
where
f prime
f
is
prime is
0 or
zero
f
or
prime
f
doesn't
prime doesn't
exist.
exist.
And you
And you
shouldn't
shouldn't
include x
include
equals
x
0
equals zero
automatically. I
automatically.
mean, the
I mean,
only
the
reason
only
you
reason you
include
include
the x
the x
value
value
0
zero
is
Dr.
is
Kim,
if,
if
yeah,
yeah.
we're getting a lot of feedback and we can't really hear you.
okay.
Okay.
Let
Let
me,
me
hang on just a
hang on
second,
just a
folks.
second, folks.
All right, is this any better?
Speak again, please.
Yeah, can you hear me any better now?
Oh yeah, this is bad.
Okay, sorry about that. Let me start over. I'm so sorry. Okay. Um, just announcement wise, please do the pretend quiz, the practice quiz before the actual online quiz. The online quiz, just do it anytime today. It's not meant to take you a long time. It's supposed to be one question, but just at some point, just sometime today. Okay, the key thing we ended class on yesterday was an inflection point. Is this point in the graph where the graph starts concave down and goes to concave up, or starts concave up and becomes concave down? That one point where that transition occurs is called an inflection point. I think what was actually going on, not that you have to unmute to say this, is I wasn't speaking loud enough. That was actually the problem. Is it still a problem?
No, it's fine now. Thank you.
Oh, okay. Sorry, I saw a comment pop up. Okay. All right. Okay, so this is stuff from before spring break, but I wanted to just remind you that so don't write all this stuff down. You have this. But sign chart for f prime, you build this by making partition numbers for f prime. You don't want to just automatically include x equals 0. Yeah, don't include x equals 0 automatically. Instead, you only include those x values where the derivative equals 0 or the derivative doesn't exist. Just those x values. And then having drawn just those x values on a number line, then you pick some x values in between to test just to see is f prime positive or negative. And then based on that, and maybe this is a thing that I just wanted to clarify, that the sign chart for f prime tells you where f increases or decreases. Now, the only real difference in the technique for a sign chart for f double prime, there's nothing really different. In fact, you can see what I really did was I just copy pasted, just changed all the f's to f double primes. The only thing that's really different is at the end over here, there's a concavity of f. That's what, so when you know that f double prime is positive or you know f double prime is negative, that gives you information about f. It tells you when f is concave up or concave down. So you'll find that quite a lot of what we do today in principle is review of some stuff yesterday. But what you're going to actually see, I think, today is that there's a good reminder of some of the calculus that kind of gets forgotten. Things like the product rule and chain rule, these sorts of things come up a little bit today. So that's good review. And then the other thing that you'll notice comes up quite a lot is there's kind of a lot of algebra. There's a lot of algebra that that we did look at actually way back in the first, or sorry, the 0th web work assignment. The algebra review had this type of algebra, but ever since then we actually haven't been using that kind of algebra. So okay, just to get us started, just to get our feet wet, let's take a look at the function f of x equals x cubed. We'll determine the concavity just as a small example to get started to review. We're going to need the second derivative, so we'll have to compute the first derivative anyway, not that we need. Okay, so 3x squared, and then use the power rule again. You'll get 6x for f double prime. Okay, so we don't really need the first derivative. We only needed it to compute the second derivative. And we ask ourselves, in building a number line for f double prime, where does f double prime not exist? Where does f double prime equal 0? There's no dividing of it. There's no division going on, so f double prime actually always exists. There's not an x value you can plug in where you're not going to get an output for f double prime. Where's f double prime equal to 0? Well, we just computed f double prime to be 6x, so let's set 6x equal to 0. That equation's rather easy to solve, right? Divide by 6 on both sides and you get x equals 0. So here's what the sign chart looks like to start. For f double prime, we have sorry if it sounds like I'm repeating myself. I just want to make sure we're all clear, because instructor unfortunately does is different. These sign charts are not like standard throughout calculus, unfortunately. So the way I just for consistency, I'm putting an x value down here. That's my x equals 0. And then when you plug in 0 for x, the 0 up here is saying that the value of f double prime equals 0. So this 0 that I'm pointing at right now is actually 6 times that 0. Okay. So we're now that we know the one place where f double prime equals 0, because we solved this equation, we need to find out what happens to f double prime over here and over there. So we'll pick some values. Nice enough values to pick for x are -1 and +1. So I went ahead and plug those into f double prime. And you'll see that when you plug in -1, for instance, the f double prime is a negative. And then when you plug in x equals 1, f second derivative is positive. So we can update the sign chart to have that minus sign and that plus sign. Okay, and then the whole point is that information about f double prime, whether you have a positive or negative for f double prime, tells you information about the original function f. So you'll notice in this sign chart over here, this is in this final sign chart, this is about f, and it's not really a sign chart, I guess it's a concavity chart. And so the minus sign that applies here for x values smaller than 0 for f double prime corresponds to a concave down for f. And then the plus sign for f double prime means in the same region for those same x values, f is concave up. And then it was a chance to review in this small example that when you have a change from concave down to concave up, that's when you have an inflection. So if we were to graph this, and you're going to see a graph of this on the next slide, there's going to be an inflection point when the x coordinate is 0. All right, so I hope that's all right for a small-ish review. What I did on the next slide was I didn't copy the f double prime sign chart. I think the information we need is in this f sign chart, so I just kind of copy-pasted that at the top of the next slide. And then I just wanted to show you, just if maybe it's a little more obscure from algebra, what the graph of y equals x cubed looks like. We all recognize y equals x squared as a parabola. Y equals x cubed looks something like this. And there is an inflection point we had mentioned at when the x coordinate is 0. So in this picture, the inflection point is a point. So the point where there's an inflection is this point, right? The x coordinate is 0 and the y coordinate is 0. This 0 actually is by plugging in. I've got space here, so I'll write this in. To compute f of 0, you got to plug it into this thingy up here. You have 0 cubed. So this 0, this 0 is copied right there. Okay, and I hope you see this in the picture as well. There's a concave up part here. This part, come on, let me write. All right, okay. So this part right over here that I'm highlighting, kind of thickening right now, that part is concave up because it looks like that cup, that shape that we described yesterday. And then this part that's in the third quadrant down here, that's that frown-like shape, or rather half of that frown shape, and so that's the concave down part. All right. Here's a second example. Our function here is f of x equals x times e to the x. So this is it's time to be careful. I even said the word times, even though there's no multiplication symbol. Just like the last question, we need the second derivative, but we're going to need the first derivative first, right? And to compute that first derivative, please be careful. We have to use the product rule. There's just no way around that. So first times derivative of second plus second times derivative of first. Right? Why don't I pause, give you a chance to write down f prime of x yourself, and then I'll reveal the next slide. Just give you a moment. All right, so here's what I had. Oh yeah, put this reminder here for people who need to join later that this was done by the product rule. So first times derivative of second, so x was just copied, and then the derivative of e to the x, I remind you, is e to the x itself, right? That was the one function that's its own derivative. Sometimes people try to use the power rule, but that doesn't apply to e to the x. And then the second, so plus the second, so plus the e to the x times when you differentiate x, you get a 1. Of course, you don't have to write that times 1, but I just wrote it in for emphasis right now because we were using the product rule. I would like to actually sort of ask you to pretend that times 1 is not there right now, because now it's time to take a second derivative. So to take us another derivative, well, it's a good thing we've got a plus sign because we get to differentiate that, and then we get to differentiate the e to the x. I said to sort of ignore the times 1. We get to differentiate each of the two terms separately. So the first term we need to differentiate here is x times e to the x. See, the plus signs are great. Right? You get to differentiate one term at a time. And well, when you differentiate x e to the x, that should sound familiar because that's what we differentiated in the first place. So we actually get to copy our work. So here it is, right? So here's the second derivative. So when you differentiate x e to the x, what I just underlined, the first term from f prime, you get the work that we just did. It was x e to the x plus e to the x times 1. So I underlined in f prime the thing that we just differentiated, and I underlined the result of that derivative in f double prime. And then finally, there's this e to the x. That's the next term, and you got to differentiate that, and the derivative of e to the x is itself. This step might be a little confusing, so I just want to make sure we're okay. I'm going to pause, ask for questions. Again, what's going on here? I've kind of kept two things underlined. The underlined thing in f prime is x e to the x. The derivative of that is underlined in f double prime. So I hope we're doing all right. So we ask ourselves the usual things. Where does f double prime, in building a sign chart for f double prime, where does f double prime not exist? Well, there's no dividing going on, so there's no concern of f double prime not existing, so that we're not going to get any x values on our sign chart due to that issue. So then the other thing is, well, what about where is f double prime equal to 0? So we'll set this, what we just got for f double prime, we'll set it equal to 0. Okay, this is now, you're going to see sort of a taste of the kind of algebra we deal with in these types of problems. Okay, so this is the algebra from WebWorks 0. In fact, I would maybe ask you to go back and look at WebWorks 0, not to do it for credit, but I think you'll find some really strange things in that I actually took some functions, took second derivatives, and then just set those equal to 0. And back in, I didn't frame it in the language of derivatives, of course, but back in WebWorks 0, that's what I did. I started with a function, I took a derivative twice, and then I set that equal to 0 and asked you in quite a number of WebWorks questions solve the equation. And there was some really kind of freakish fractions that appeared that way. Anyway, let's solve this one. There is an e to the x plus e to the x, so if we combine like terms, you'll have a 2e to the x there. And here's the thing. There are two terms here separated by the plus sign, and both of the terms have an e to the x. The name of the game, as you heard yesterday and heard before spring break, is to try to factor as much as possible. So since both of the terms have an e to the x, let's factor that out. You have an e to the x outside of the parentheses. Whenever you factor, you always draw a new set of parentheses. So you have an e to the x outside the parentheses, x plus 2 inside parentheses, and then we get to set each factor equal to 0. Right, so whenever you have two things multiplied, so that's one thing, the e to the x, here's the other thing, x plus 2. Those two things are multiplied together, set equal to 0. You get to set each individual part equal to 0. That first equation, e to the x equals 0, actually has no solution. The reason is that e to the anything is always positive. E to the x, whatever you plug in for x, e to the x is always positive. So if e to the x is always bigger than 0, how could it ever equal 0? So this first equation right here, right there, has no solution. So the other equation, x plus 2, well, we'll just subtract 2, of course. And then, so that's the only x value we're going to include on the f double prime sign chart. Don't include x equals 0. So here it is, right? So f double prime, you see that x value of -2 below. When you plug in -2 back into f double prime, so whether you plug it in right here, or this is also a version of f double prime right here, where you have e to the x times quantity x plus 2. Wherever you plug in that -2 into either version of f double prime, you get f double prime of -2 equals 0. All right. now what we need to do is figure out what's going on to the left of x equals -2 and to the right of x equals -2. So I picked x equals -3 as the x value to the left. And then I could have picked x equals -1, but I just really didn't freaking feel like writing more minus sign, so I just picked x equals 1. I could have picked x equals 0, but I thought that might have looked confusing. Keeping in mind that e to the whatever is always positive, so e to the x is always positive. So even when we plug in this -3 for x, and I see this e to the -3, don't be tricked by that. E to the -3 is positive, because e to the anything is positive. So here we have a positive times a negative. What's in parentheses is negative. Positive times negative is why we have this negative, or this less than 0. E to the 1, again, e to the anything is positive. So here you have for f double prime of 1, you have a positive times a positive. So here's our updated sign chart for f double prime. We've got a minus sign and a plus sign. And then, of course, this tells us information about f, right? So the fact that f double prime is a negative means that f is concave down. So for x values to the left of -2, f is concave down. For x values to the right of -2, f is concave up, because f double prime is positive. Maybe one last comment I'll make here is that I plugged in back into the original f way at the top. I plugged in -2 for x and learned that f of -2 is equal to, -2 times e to the -2. That's the y value here that I just circled. And because we have an inflection, right, in f, there's a change from concave down to concave up. So we have this inflection point, and just to emphasize that an inflection point is a point, we have down here, the x coordinate is -2. The y coordinate is what we just computed. I'll circle that again. So this -2, e to the -2, this is an inflection point. It's in fact the only inflection point for this function. Hope we're doing okay with that example. Maybe I'll pause, see if anybody has a question and wants to unmute a mic. Get a swig of coffee. Okay. The next example, I don't want to go all the way through because I actually have another example that I want to do all the work on. So for the next example, I really just want to get to the step of getting the x values. So in the next example, it's really meant to serve as an excuse for algebra review, but I'd like to kind of get to that sort of step, right? So the algebra game is going to be a little strong. And so please don't hesitate to ask questions. I think, these are the things that come up all the time for folks. So the function we're going to work with right now is 3 over x squared plus 12. And the language here I'm using is find the partition numbers of f double prime. In other words, right now, what we're finding is which x value should be listed at the bottom of the number line for f double prime. And then beyond that, we're not going to work on this question due to the interest of time. I think in fact, if you look at the work, you'll be set up in a good place to finish the question or to do the other parts yourself if you wanted to look at concavity. But I wanted to show you how the algebra gets. So we need a first derivative and take a look. I mean, we've got a fraction, right? So we can't just differentiate the top and bottom separately and call it a day. We've got to use the quotient rule. So I know it looks a little messy, right? But bottom times the derivative of the top, that top 3 is a constant and differentiates to a 0, minus top times derivative of bottom. So the 2x in parentheses is the result of differentiating x squared plus 12, because after all, the 12 part when you differentiate is a constant, all over the denominator squared. Since we do have 0 times something right over here, and 0 times anything just goes away, I thought I'd also simplify the 3 times 2. So you have this. Normally I don't focus on cleaning a derivative, and I know that like for exam 2, people, whenever they ask, they're like, do I need to simplify this? I'm like, no, don't even worry about it. But if all you needed to do is compute a first derivative, yeah, don't simplify, leave it like this. But because we need to do another derivative, we make our own lives easier by kind of simplifying by cleaning things up first. Okay, this next derivative, we've got to use the quotient rule again, but in the process of using the quotient rule, you're going to see another derivative rule pop up in the process. So here we got it. So there's the bottom. There's the x squared plus 12 to the second power, and then times the derivative of the top. So what I just circled right now, that is the derivative of the negative 6x that was up here. And then this minus sign that I'm circling is that's the minus sign that's in the formula for the quotient rule. Then you have the top times, and I actually just, when I was designing the slides, I realized it might be a little easier if I draw on the multiplication symbol that I pointed an arrow to right now. You don't have to draw that multiplication dot, but the point is we now need to differentiate the bottom. And the bottom says x squared plus 12 quantity squared. To differentiate that, we should use a chain rule. I'd rather not FOIL this out. I'd rather just apply, one option is to FOIL using algebra and then differentiate, but I think the easier option here is really honestly to use a chain rule. So you have 2 times x squared plus 12 raised to the first power, and then the chain rule requires to differentiate the inside thing, and the derivative of that x squared plus 12 is a 2x. Oh, so there's a lot there. And this is all over the old denominator over here, but squared. So the squared I just already took care of and wrote a 4th power instead. How does that look for the second derivative, folks? I want to see if we've got any questions about that first. Okay, as far as finding partition numbers for f double prime, for those x values to put on the number line, we ask the usual 2 questions. Where is f double prime equal to 0? Where does f double prime not exist? The fortunate thing here is the denominator is never 0. See, the only way you'd get like an undefined is if the denominator were 0. But the denominator is never 0 because you've got, first of all, x squared. X squared is never negative, right? X squared is a positive number, or maybe 0 at the smallest. Then you add 12 to it. Then you raise that to an even power. So you never get a number that's 0, no matter what you plug in for x. Even if you plug in a negative number, that denominator is always bigger than 0. So you never have a danger of dividing by 0. F double prime is always defined, or rather, F double prime is never undefined. The only other thing we should do then is, the only place where we're going to get any x values for our number line is by asking what x values would you plug in so that the result is equal to 0. So when is f double prime equal to 0? Well, here, let's just take the f double prime that we just got and set it equal to 0. So it's all this step is just taking that work there, what we just got for f double prime, set it equal to 0. This looks like a mess, I admit, but here's where the algebra game is rather strong, and you'll see a lot of this kind of thing in web work and quizzes and exams, and so it's just kind of the nature of how these questions go. To solve this equation, whenever you have a fraction in an equation, I think the easiest thing to do is multiply it by a denominator on both sides. So if you multiply both sides by x squared plus 12 quantity to the 4th, then on the left side those cancel, and on the right side you have 0 times, well, 0 times whatever is 0 anyway. So what looks like occurs is that just the denominator just disappeared, but it's not that the denominator disappears, it's just you multiplied by the denominator on both sides, so it canceled on the left. A couple other comments I guess I should point out. This negative 6 that's here, I just moved it in front. And then the other thing I did was the minus that's here, I turned that into a plus. I took care of simplifying some of the numbers, so you have a 6, a 2 right here, and then another 2 over there, and I just multiplied those all together to give you that 24. I also saw an x and another x floating around, and that's why there's an x squared. So there's a little bit of algebra simplifying that already occurred, and now this equation still looks like a mess. I think this is the place where I noticed from the past that people tend to freeze up, and I don't want you to do that. I want you to always keep in mind the thing that we've already been saying about these kinds of equations is to factor. So there are two terms. I put this text here as a reminder. If you look at the slides later, I use the word both, and I use that very intentionally. There are only two terms. Terms are separated by plus or minus signs. This is the only plus sign that counts. The other plus signs are stuck inside parentheses, right? So what can factor out of both terms? Well, I see like a 6, in both of these. Like 6, there's a 6 hiding in the 24. I also see an x squared plus 12. Right? Over here, there's actually 2x squared. There's two of them. There's 2x squared plus 12s. But we can factor out one of them. And when you factor out, you get a thing that looks like this. So I factored out the 6. I factored out the x squared plus 12. When I made the slides, it looked a little funky to me. So I drew a set of parentheses way larger. Just like I commented in an earlier example today, whenever you factor, you always draw a new set of parentheses. So this new set of parentheses is drawn larger. And then what's left from when you factor should go inside the parentheses. So you'll notice this plus sign here is that plus sign. And what was left out of the first term was the minus sign had not been accounted for yet. That's why there's a minus sign here. And then there were 2 copies of an x squared plus 12. So that extra copy is right there. For the other term, the x squared plus 12 is already accounted for way back here. We factored it out. What hasn't been accounted for is the x squared, so that's written down. And then the 24 was much bigger than the 6. It was, in fact, 4 times bigger. So I think all the pieces are there. Sorry, actually drawing all that probably makes it look a little too messy. But the point is, if you step back, sorry that maybe I shouldn't have explained too long on it, but all that really happened here was quite a lot of factoring. At this point, people then tend to go, now what? Now what? Now how am I supposed to solve this equation? I would encourage you to keep factoring. Now, actually, to factor right here, every time you factor, it becomes easier to notice additional factoring that might occur. But here, it's actually going to help to first unfactor, to first distribute the minus sign. Then it'll be actually easier to spot some additional factoring. So let me distribute that minus. Nothing much changed here other than a minus in front of the x squared and a minus in front of the 12. And then you can even combine the negative x squared and the positive 4x squared. So I wrote the 3x squared first, but now take a look at that, right? In this set of parentheses, 3x squared minus 12. That factors. Factor out a 3, right? Both the 3x squared and the 12 have a 3. Factor that out. So there it is. The 3 is factored out, and what's left inside the parentheses is an x squared minus 4. X squared minus 4 factors even further as x plus 2 times x minus 2. It's a difference of squares. So I highlighted the key word in blue. The name of the game here is factor. Factor, factor, factor. So now let's go ahead and solve the equation. So first of all, you do have in this line above, you've got a bunch of things multiplied together equaling 0, so you get to set each individual piece equal to 0. When you set 6 equal to 0, that doesn't give you x equals 6. 6 equals 0, there's no value of x that's going to make 6 equals 0, so there's no solution to that. X squared plus 12 equals 0 has no real solutions. If you started subtracting 12 on both sides, you get some imaginary solutions, but it's calculus, we just keep it real. 3 equals 0, likewise, has no solution. When you set x plus 2 equal to 0, when you set x minus 2 equal to 0, those are the only places you get solutions. And so the solutions you get are x equals negative 2 or x equals positive 2. Okay, so I know that was a lot of algebra. So maybe I'll pause, find out if there's any questions. And I mean, the point is, that's all I wanted to do in this question. I just wanted to find out what the partition numbers, when you draw out a number line, which x value should you label below, and it's only negative 2 and positive 2, no other x values. The rest of the work, if you wanted to extend the question, would be, find out where is f concave up or concave down. But the main point of this question was just to talk through a little bit of the type of algebra you can expect to see. All right. I would like to do really just one more question today. Now, I'm gonna say the following about this question. There's a lot of pieces, and what I have learned about this kind of area, this chapter that we're in, is there are questions that are good for in class. in the sense of like they help explain what's going on, and they're not good questions for quizzes or exams. So why show them? Well, it's because they're the best for explaining what's going on. What happens is often the questions we do in class need to be a little more tedious because I need to use a question to show a lot of the strange behavior that goes on. The downside a little bit is I don't want you to tune out. Like the whole point is these are good questions to ask in class. I don't want to ask the tedious questions to you in a quiz or exam. Even in homework, I'm trying to minimize some level of tediousness, but you do need to see some of it. The point is, I wish there were example of questions out there where all the parts turned out super nice, but it turns out in this particular area of calculus, if one part of the question is nice, usually another part is not so nice. And so you're going to see a little bit of that in this question. You're going to see me, in fact, use a calculator in a couple moments just because it's going to make it easier to talk through what the hell is really going on. So please forgive me about that. We've got this function that has a couple fractions in it. X to the fourth over 4 minus x cubed over 3 minus x squared over 2 plus x. And there's a couple tasks. First, use the information from f prime to find out where f is increasing or decreasing. Then take those critical numbers, find out where we have local mins or maxes, and then also use a second derivative to find out where f is concave up or concave down. So I don't really want to use a quotient rule, to be honest. You can do it. It'll work. But the thing is, since those denominators are just plain numbers, I wanted to just use algebra. So there's no f prime yet, right? That's what I'm pointing to right there. That just says f. There's no f prime. I just rewrote by scooting that 4 in the denominator. It's still in the denominator, but I wrote the 1/4 off to the side. The whole point is now each of these terms, I don't have to use a quotient rule. I don't even have to use the product rule. I just use the constant multiple rule. You get to copy the 1/4 and then differentiate x to the fourth. When you differentiate x to the fourth, of course, you get 4x to the third. So that 4 in the 4x to the third is going to cancel with the 1/4, the 4 that's in the denominator there. So you actually end up, that first term is going to differentiate to become x cubed. That similar argument works for the next term and the next term as well. So you should get, at least in a very, very clean version of this function, f prime, you'll get x cubed minus x squared minus x plus 1. Okay, so since the first part of the question does say to use information from f prime to find out where f is increasing or decreasing, we should ask ourselves the usual questions here. We need to build a sign chart for f prime. Okay, there we go. Look, f prime always exists. There's no dividing by 0. So let's set f prime equal to 0. So set x cubed minus x squared minus x plus 1 equal to 0. And I will spare you all the factoring work here. It can be done using factoring by grouping, but you'll end up with x minus 1 quantity squared times x plus 1 equals 0. The point here being that you can set each of these pieces equal to 0, and you get these two x values. X equals -1, x equals +1. Those are the only two x values that you see on the f prime sign chart. So down here, don't include a 0 down here. Okay. If you include a 0 here, it becomes super messy. So I'm going to erase what I just wrote. If you include 0, then people tend to automatically include 0. I know it's a habit from drawing number lines in the past. But then it's like, what x value do you pick? You'd have to pick like 0.5, and that's just extra painful. So if you include 0, it becomes challenging to use nice x values. The point is by not including 0, because it shouldn't be included. We didn't get x equals 0 up here. Then it becomes real nice to pick values of x to use. I went ahead and used x equals -2 for this part over there. I used x equals 0 and then x equals +2. And I should take a moment to explain where the hell did I get this. I used what I'm boxing right over here. That is f double prime. And same deal over here. You might wonder, how did you get f prime of 0 is equal to 1? I actually went back to the other form of f double prime, f single prime, which is right here. So you can mix it up, like if you just need to find out whether f prime is positive or negative, usually the factored version is usually nicer, but because we're plugging in x is 0 in this case here, it was kind of just convenient enough to use the original version of f prime as well. So you do whatever you need to do to find where f prime is positive or negative. And so then we can update the sign chart. So we have this number less than 0 or a negative. We actually computed the number, it's 1, but that's a positive. And then a number that's bigger than 0, that's positive. So a thing, just like before the break, I wanted to point out is you don't want to assume that you just have this alternating of pluses and minus signs. That doesn't always happen. So you just kind of got to test it and see what, because you see how you have 2 plus signs in a row here. And then information about f prime tells us information about f. So the minus for f prime tells us f is decreasing. The plus for f prime tells us that f is increasing. The plus for f prime tells us for f you have increasing. Finally, let's go ahead and talk about this classifying critical numbers. Like the formal way to do this is using what we've called the first derivative test. I would just like to, instead of quoting it directly, I want you to picture what's going on. If you have decreasing first, and then you have increasing next. So in the picture, if you were to graph the function, I'm not even going to draw axes, because I don't know exactly where the function should be drawn. But the point is, as you would start drawing, if you've got decreasing, then increasing, well, this is what decreasing looks like, right? And then this is what increasing looks like. So right at the bottom right there is where you have a local minimum, right? So if you have a decreasing part, I'll sort of zigzag draw that. This is the decreasing part. Then at the bottom you have this valley, so you get a local min. So that already answers actually this part. If you have increasing and then increasing yet again after, well, you don't get a local min or a local max. It's sort of like you're climbing a hill, you take a little break from climbing, and then you keep climbing the mountain. That's not a peak or a valley. Okay. There is a second half of this question, which is the third part of this question is asking where's f concave up or concave down. So that's going to require the second derivative. We already computed the first derivative. I know I've run out of space on this slide, so on the next slide, I copied the original function f, I copied the f prime that we computed, and now let's take a second derivative. So when you differentiate x cubed, power rule 3x squared, differentiate x squared, power rule, you get a 2x, differentiate x, you get a 1, and then when you differentiate the 1, well, that's a constant, you get a 0. So this f double prime is always defined because there's no dividing by 0 or any concern of that kind. We ask where's f double prime equal to 0, so let's set this equal to 0. I know that this one's a little more challenging to factor due to the fact that there is this 3 in front of the x squared. If you kind of poke around at this, you can eventually factor this, or you can do things like apply the quadratic formula because the highest degree is a 2. And even if you use the quadratic formula, it'll hint at what the factoring should be. But if you kind of guess and check a little bit at the factoring, you should get 3x plus 1 times x minus 1. So the point being, what's written here is just another version of f double prime. And we can now set each factor equal to 0. You'll get these two values of x, right? One of them is x equals negative 1/3. The other is x is equal to 1. Those are the only two x values that we're going to draw on a number line for f double prime. So those two x values are shown below. The value of f double prime is 0 in each of those cases, so those zeros are written above. Now we need to find out what happens in between. So this question I did pick very carefully. It took me a long time to come up with this specific problem. But I picked this problem because I knew that these f double prime, the x values here would be super nice because we need a number that's between negative 1/3 and positive 1. And a nice convenient number to use is actually going to be x equals 0. So for the x value over here, I picked negative 1. So you can, maybe I'll give you a moment to stare at my f double prime computations, but I plugged in -1, 0, and 2 for my x values. See if everything there looks all right to you. Okay, so now that we've got this bigger than 0, less than 0, bigger than 0, we can update the sign chart with a plus, minus, plus. So knowing the positivity or negativity of f double prime, then as usual tells us something about the original function f. So the plus sign for f double prime, I decided not to draw a number line version of f. I thought I'd kind of write it out a little bit more in words this time, more like yesterday, to look a little bit more like what you'll type into WebWork. So the plus sign that occurs here for f double prime and the plus sign over here, those x values are mentioned by writing interval notation here. So here's where f is concave up. The minus sign for f double prime is where f is concave down. So f is concave down on the interval -1/3, 1. Okay, we're actually done with all the parts of this question, but what I just kind of wanted to comment is, just like we did yesterday, and I don't want to spend a whole lot of time doing this right now, but I just want to comment that, so like, the -1 should be, I put the f prime and the f double prime sign charts that we just got all kind of here visually, but -1 is to the left of -1/3. And this minus for f prime means f is decreasing. The plus here for f double prime means f is concave up, and so on. So you've got to kind of stare at this carefully to see where did all this information for f come up. But then this will tell you something about what kind of shape the graph of the function should have. So what I actually did was, on this slide, there wasn't a lot more room for what I really wanted to do. This information was used to create this information about f. I just put this information about f here at the top of the next slide. And now the point is, these three x values of -1, -1/3, and 1 are rather special. Something is happening there, whether it's a change in concavity or f went from decreasing to increasing. Always something is going on at these three special x values. So I just wanted to find out what specific points we have in the graph. And here's the part where I confessed earlier I used a calculator. I went ahead and went back to the original function, which is hiding up there at the top in blue, and I plugged in -1, I plugged in -1/3, I plugged in 1, and the numbers are messy. I mean, every time, there's because you've got denominators of 4s and 3s, so, common denominator of 12. I mean, in decimal form, these numbers are messy. And so these are approximate y values. But the point is, here's what a graph looks like. This is just, again, this is an accurate picture. I put this into a graphing calculator, screenshot. The point is, when x is -1, the y value is -0.9. So I drew in this point that's down here, that valley first. And then this information corresponds to this next point right there. And then when x is 1, the y value is a little bit under a half. So sorry, I didn't label the y-axis because it started getting a little messy. But the whole point is, these 3 points are kind of special. So I went ahead and plugged in for the actual y values first, and then the whole point is I want you to see this going on, that when x is less than 1, the puzzle piece, the Lego piece we have here, is decreasing and concave up. The next puzzle piece that's right here is increasing concave up. I just kind of want you to see how these pieces look. So if you find out where f is increasing and decreasing, you find out where f is concave up, concave down, then you can compute specific points where some kind of transition is occurring. That kind of helps anchor the graph. And then you can connect the right shape of puzzle piece for each of these, right? So decreasing concave up looking like that, increasing concave up looking like this, increasing concave down looking like that. And so you'll see a shape that looks like that here, and then increasing concave up looking, whoops, that looks like a little decreasing part there accidentally, increasing concave up looking like that. So you see a piece that looks like this here. So it takes a lot to put all these pieces together, and again, it's easy for me to what I usually do in a quiz or exam setting is I try to pick a function where you have to, for one function, you're going to look at concavity issues, and for a totally different function, you're going to look at increasing, decreasing, so that I can remove the burden of having anything too tedious. But I just kind of wanted to show you that in one function, you usually get quite a bit of the tediousness. I should point out one last thing here is that because there's a change in concavity that occurs right here, concave up to concave down, and then you have a change in concavity, concave down to concave up, those are places where you have inflection. So there's an inflection point, right? Let's see. So it occurs at this x value of -1/3. So that's an inflection point. The arrow that I'm pointing, that's an inflection point, and there's an inflection point. So if you look to the left of one of those points, you have a concave up or a concave down, and then to the other side of that point, you have the reverse. I'm just going to mention kind of one last thing and then an announcement. So if you have an x value c that's a critical number, and the derivative is equal to 0, then there's this new thing called the second derivative test. We're going to practice this through the rest of this week. But this is just another way to get local mins and maxes. So we had the first derivative test. Now, if the second derivative is positive, then f has a local min. If the second derivative is negative, f has a local max. Now, this seems strange. I think people go like, wait, why is the positive thing corresponding to a minimum? But it actually makes sense if you think about, so f double prime positive, that means f is concave up. And let's think about how concave up looks, like this. And if you have that cup shape, then right at the spot where the derivative equals 0, which is right there, that's where the slope is 0, you have a local minimum. So I put a lot of words to this at the place where f prime is 0. You have the bottom of a valley, that's a local minimum. Same thing the other way around. If f double prime is negative, that means that f is concave down. And that means that the shape you've got is like this, right? So that's what concave down looks like. And right where f prime is 0, that's right where the slope of the tangent line is 0. That's where you have a local max. Again, all of these ideas, like this f prime equaling 0, the thing I want to remind you of, the thing I don't want you to forget throughout the remainder of the semester is that the derivative is a slope. Derivative is a slope of a tangent line, to be specific. Okay. The main announcement I just wanted to make sure to have reminded you of is to please do the online quiz today. And I think that's it. We'll end here unless there's questions. Thanks for your patience today with the technical difficulties.